We're going to talk about some of the scariest words in physics. One is quantum. You know that's a scary word. Relativistic is a scary word. But the word that makes those scarier is field. Quantum field theory, relativistic fields. The word field, for some reason, sounds intimidating in physics. So what we're going to do first is just convince ourselves that at least mathematically, a field is not so bad. So let's look at a field and work our way towards a nice definition. So think back to when you took algebra. Maybe it was 5 years ago, maybe it was 50 years ago. And the first thing you talked about in algebra was a function. Function was simply you have an x-axis here, a bunch of values of x, and for each one you assign it f of x. The simple idea of a function. Maybe it's a table of numbers, maybe it's a mathematical formula that gives you the f of x for each x, and you can plot it and it looks something like that. So functions, I'm going to assume you're very happy with. What if we had a function of 2 dimensions? Here's y, here's x, but we could still plot f here, and it would be f of x and y. For each x and y, there could be a unique f, and it would make, if I plotted it, its height is f, just like I did here, but in 2 dimensions, it might look kind of like that. It might have a nice little shape like that, where each point here has a corresponding x and y. So what is that? That's a function in 2 dimensions, but I would call that a field. So really a field is just a function in higher dimensions. You could think of it as we have a field of values here. We have a field of x, y values, and each one of them has an f. So really mathematically, field doesn't really mean anything beyond function. Just generally as we talk, we call things in 1D functions. We might call things in 2D fields. Although in physics, actually, we call everything everything. It doesn't really matter. And you might say, well, what about 3D? Could you have a 3D field? And the answer is yes, of course you can. X, y, and z, and now it becomes hard to draw. Okay? So here, if I were going to draw this field by saying the size of the circle represents the size of f, I could have a big circle right here and have the circles get smaller as I go farther away there. And I could try to give you some idea of a 3-dimensional thing in space, like that. Okay? You can imagine this function, or this field in 3 dimensions gets really big right here and it's small everywhere else. That's one way I could attempt to draw f of x, y, and z. All right? So if we wanted to go with one of our simple little definitions, let me write it down here, this is a field. The definition would just be, for the purposes of this class, a field is just a function of 2 or 3 dimensions. That's all it is. Okay. Oh, so I see we have a question. Let's see. Belieber 2237 asks, the fields are scalars. The fields I showed you, these fields are scalars. Can fields also be vectors? So the answer is yes. So the things I drew here were scalar fields. I just draw height as a function of 1D. I drew a surface in 2D. That's again just a height. And when I drew the 3D field, I drew circles with a certain size. Those are all scalar numbers. But yes, you can have a vector field. You can have each point in space a vector pointing different directions. So you can have a position in space and the vector pointing in a different direction. And that's where fields start to get hard, when you have vector fields and you try to do calculus with them. But just to get started, keep in mind that a field really is just the old function that you're used to. Philosophers. Let's think about philosophers for a second. Philosophers ask difficult questions that nobody really cares about the answer to. One of the most famous philosophical questions, I think, is if a tree falls in the woods and no one is there to hear it, does it make a sound? Right? So the philosopher might say, well, maybe sound is a communal experience between the tree, and the answer is no. Physicists would say, of course it makes a sound. Okay? When a tree falls in the woods, it releases energy into the air. That energy vibrates the air molecules, creates a pressure wave, and that pressure wave is sound. And it's there whether your ear is there to hear it or not. Okay? So we have something similar with electromagnetism. So let's think, instead of a tree, let's think about a charge. A big charge Q sitting here. And let's imagine, what if there's a little charge, little q, here? And let's say they're both positive. What's going to happen is you're going to have a force on little q. It's the force we calculated before, that big Q would apply to little q. I could put little q here. And you'll also have a force. It'll be bigger because we're closer, as we learned from Coulomb's law. I could put little q way over here. Little q right there. And it would have another force. The force is always going to point away, as we learned with Coulomb's law, and it would be smaller. I could put little q anywhere around big Q, and I would generate force vectors. And in fact, I would have a force field. So that's a case of a vector field. All the vectors, as you move around, will get smaller as you move away from big Q, and they'll always point away from big Q. So that's an example of a force field. But now let's think about the philosopher's question. What if little q isn't there? Okay? So big Q is creating a condition where if little q is there, it feels a force. But what if it's not there? What is it doing? Is it doing anything? Well, just like sound exists anyway, it is doing something there. It's creating an electric field. That's how we think of these forces when only one of the charges is there. There's no charge to experience the force, but it's modifying space there and creating a condition which will lead to a force. So our simple definition is the electric field could be called what a charge does to space is sort of a interesting way to put it, what a charge does to space. Let's think about it mathematically now. One reason we want it to define it mathematically is because physicists are actually lazy, is because we don't want to have to calculate the force every time we have a different value q, little q here. We want a general number that always tells us the force. So that's why we calculate E, the electric field. Okay? The electric field created by big Q doesn't actually care what size little q is there. It's just doing something to space. So the way we do that mathematically is we define the electric field. So I'll use 3 bars, which means we've defined it that way, as the force that big Q would apply to little q divided by the quantity of little q. So really, the electric field is just the force per unit charge, the force per unit of this little charge here. In books, this will often be called the test charge. And the reason is we're moving little q around to test the force that you would get in each location. And here what it's doing is giving you a number that's, or a value that's useful, that doesn't care what little q out here. Any little q you put out here, no matter what its quantity, you can now get the force just by multiplying by the electric field. The unit for this is Newton per Coulomb. So the unit of the electric field has no fancy name, hasn't been named after anyone, it's just a Newton per Coulomb. You'll often see plots of the electric field, and they're often very complicated, but you can actually generate them yourself just by thinking about the force. So here we have, say, a positive charge and a negative charge. If you want to start drawing the field, you just have to imagine how you have a test charge. What if I put a test charge here? What force is it going to feel? It's going to feel a force that way, right? A positive charge would fly away from the other positive charge, or repulsive force, and an attractive force towards that charge. A little test charge would feel a force like that. So I just drew the force, but I also drew the field, right? The vectors point in the same direction. All you're doing is dividing the force by a scalar number, which is the quantity of the test charge. If I put it here, put the test charge there, normally the force would just be straight up, right? Be straight up because we just apply Coulomb's law. However, it's also attracted this way. So you do a little vector addition in your head, a big force pulling it up, a somewhat smaller force pulling it that way. Therefore, it's kind of like that. And then down here, it would be the same thing. It'd be kind of like that. All right. What if I put it here, right in the middle? Then it's going to feel a positive, or the positive charge is going to push it that way. The negative charge is going to pull it that way, and you get a force like that. And you get a similar one down here, and if it's here, it's going to get pulled straight towards minus q, but then pushed away a little bit. It's going to be kind of like that. And if you start to fill these in, you can actually draw the electric field. Since it's the force on a positive charge, it's always going to point away from a positive charge and towards a negative charge. this one would go out, and I'm running out of room, and it would come in like this. And then here, a positive charge there would go this way, and it would actually never come back. Right? So the field goes away from that charge, and it goes towards that charge. So you can actually kind of generate these plots just by thinking about forces and thinking about vector addition. All right. So that one we may add a demo later when the humidity is low enough. We've defined the electric field. We've thought about the electric field. Now let's find a formula for the electric field. Let's start with the electric field around just a small sphere of charge, or a point charge. So to start, recall Coulomb's law. Okay? So remember, we have Coulomb's law. Let's say we have a big charge plus Q here. And let's think about it like we did with the electric field. Let's draw a little charge further away, little q. So big Q and little q. So Coulomb's law told us the force between big Q and little q. So F, and we had this notation Q to Q, big Q to little q. That's the force big Q will apply to little q, equals Coulomb's constant times this charge big Q, this charge little q. And then we had to have the separation. So the separation between them, we just call R. We can call it R, Q, Q, big Q, little q, the separation between the two. So R, Q, Q squared. And then we have to have the vector direction, and that came from that unit vector, R hat. And again, we keep the same notation, subscript big Q, little q. And that meant the unit vector, so its magnitude is 1, because it's a unit vector, along the QQ axis and pointing in the direction from big Q to little q. If you get all that right, then you're going to get the force right. Now let's think in terms of the electric field. The electric field generated by this big charge. So thinking from our last lecture, we know that the electric field, we're going to get the electric field of big Q. It's defined to be the force that big Q would apply to this little charge divided by the little charge. Remember, it's the force per unit charge. Was our definition of the electric field. Now you'll notice I've changed our notation a little bit. I didn't put big Q, little q. And that really comes down to the whole philosophical point of the electric field. It's because we're not calculating really the electric field right here. We're calculating the electric field anywhere. Anywhere little q goes, that's where we're calculating it. We're not calculating something dependent on little q. So we change the name to just the E field due to big Q. So this is just the E field created by Q, independent of the little charge. It's usually called the test charge. So to find it, well, we just plug in for big F, and you can see what's going to happen here. It's going to be KE, big Q, and the little q's cancel over R squared R hat. And again, I've changed the subscripts, and not just for fun, I've changed them because it has a significant meaning. There are now no subscripts on R and R hat. And the reason is, we're now talking about any position around big Q. Big Q, basically, if that sits at an origin, we're just looking at a spherical coordinate system. So really, now we've calculated the electric field anywhere. I guess if you wanted to be specific and say where big Q is at the origin, you could call them R big Q and R hat big Q. If you wanted to specify the origin because your problem had other R's floating around. But basically now we're calculating the electric field pretty much in all of space. So this is, these two R's we'll just write down, is the distance and direction from Q. That's how you'd calculate it. What's the unit? The unit is, well, you can see what the unit is right there. It's a Newton per Coulomb. And what's funny is the unit for the electric field has no name. It wasn't named after anyone. It's just the Newton per Coulomb. We can also visualize the field now. So now we have mathematically described it. Here's our field, and you can kind of already start to see it. It's a field whose magnitude goes down as 1 over r squared. That goes down as you get farther away, just like the force. And it always points away from big Q. So let's draw that and see what it looks like. So here we have big Q. And the E field vectors now, not the force vectors, the E field vectors are going to point away from big Q. And if you get farther away, they get shorter because it goes as 1 over r squared. And if you get farther away, they get a little bit shorter, a little bit shorter, and a little bit shorter. Oh, and I forgot, I always like to draw this one too. I forgot. So I'm going to draw all of them. And you can't stop me because I am here and you are there in both time and space. There. Beautiful E field around a point charge. Is it beautiful? I don't know. It's kind of beautiful, but does it represent everything? No, it doesn't. So all the vector fields we're going to talk about are three-dimensional. You know that in reality, if I could draw it, I would have vectors coming out this way and going off that way. They'd be going away spherically from the charge, but I can't draw that. So what we're going to do to help you visualize the fields is we're going to look at them in a visualization lab and really be able to move them around in 3D to see them better. We can't do that all the time. So when you do physics, you always have to remember all these fields I'm seeing in the paper of this book are actually three-dimensional fields. When you see this, you got to see it coming out in 3 dimensions. But to get us started, we'll actually look at them in a 3-dimensional visualization. But remember, that's what that really means. So let's go to the visualization lab and see what it looks like. Yeah. Okay, it's a long walk, sorry. Welcome to the Rice Visualization Lab. This is this nice screen that will let us see our vector fields in 3 dimensions. So as I said, I draw them in 2 dimensions on the board, but to understand the physics, you often really have to think about them in 3 dimensions. So here's a perfect example. Here is a positive charge in red, and green is the vector fields pointing away. And just like I drew on the board, the farther you get away, according to Coulomb's law, the smaller the magnitude of the field, therefore the smaller we draw the vectors. And they always point away, but they always point away in 3 dimensions. So to really see it, you have to manipulate the field in 3 dimensions. So here you see, as I spin the charge around, the field always points away from the charge. So keep in mind, every drawing I do on the board is actually a 3-dimensional vector field, and you always need to be thinking in terms of all 3 dimensions. Okay, let's keep going.